Okay. So there is one more calculus rule. Let me write it here, okay? So xn converges to x in probability, just the one I said last hour. Yn converges to y in probability. Then xn plus yn converges to x plus y in probability. I'm not going to prove it, but the proof is very similar to the previous proof. All you need to do is to check that an arbitrary subsequence of this sequence has a further subsequence that converges to x plus y almost surely. Almost surely. So similar to previous proposition, use characterization theorem. Just 2 or 3 lines of proof, but I just want to leave it for you, okay? Just the same ideas, just mimic this proof, okay? So one other thing about convergence and probability is its metrizability. Okay, what is metrizability? So let's think about the real line, okay? So let's say you have a sequence that converges to x, okay, in the usual sense. These are just real numbers. So what does that mean? Well, this means you look at the distance between xn and x, and this converges to 0, right? These two things are the same. So this is the absolute value of xn minus x, and we usually call it the distance between xn and x. So the question is the following. If we have random variables and we talk about convergence in probability, can we come up with a distance function, namely a metric, on the space of random variables, real-valued random variables, such that we have xn converges to x in probability if and only if the distance, now a sequence of numbers, right, positive numbers, just numbers, such that we have this if and only if the distance goes to 0. So this is metrizing this notion of convergence, okay? So this means that you can actually see it as a metric space, okay? You have this metric, and convergence in this space with respect to this metric is just convergence in probability, okay? This is metrizing it, okay? So luckily, this notion of convergence is metrizable. Convergence in probability is metrizable, and we're going to look at what this metric is, okay? Just as a recall, so first of all, this is going to be a metric on which space, right? So let's recall that L0 is the set of all real-valued random variables, okay? That's a linear space, a vector space, right? You can add, subtract random variables and multiply them by constants. And it's even an algebra, right? You can even do multiplication. Anyway, we're not interested in that. Okay, so we would like to define a function on L0 cross L0, mapping into the positive real line, because that's going to be a distance, so it has to be positive, right? So a function is called a metric. Many of you may know this definition. So if we have a, x and y, distance between x and y is 0, if and only if x and y are equal, x and y, distance between x and y is the same as the distance between y and x. It's symmetric. And we have which property of metric? Triangle inequality. Okay, great. So the distance between x and z is less than the distance of x and y plus distance between y and z. So these are for all x, y, z in L0. Okay. So now define. So let's define a metric, okay? Just to make it a bit, just to make it different from this D, I'm going to call it dP, okay? If you measure the distance between two real numbers by the absolute value of their difference, we can do the same thing here, right? X minus y. Sorry, I forgot to put x and y. X and y. The problem with that is that this is not a number, this is a random variable. So what we can do is to take its expectation. Now there is another problem because this expectation can be plus infinity, which is not wanted in metric spaces. Where is it? Here. In measure spaces, we allow plus infinity. In metric spaces, we don't do that. So we don't want that. That's why we bound it by 1, the minimum of x minus y and 1. Now that this is a bounded random variable, it has finite expectation. It's bounded by 1, right? So this x minus y in absolute value, minimum 1, is a random variable taking values in 0, 1 interval. So it has finite expectation. So at least this part is done. It has finite and positive values. Okay. So the question is dP a metric? So I will start with B. Usually when you have an exercise in metric spaces and you want to show that something is a metric, the easiest one is the first one, right? Now it's going to be the most difficult one. Well, it's going to be simply wrong. It's not going to be satisfied. Okay? So let's look at B and C. Well, B is very simple, right? Because x minus y and y minus x, they're just the same. Is clear. So if you want to show triangle inequality, so, okay, so what you have is that x minus c minimum 1 is less than x minus y minimum 1 plus y minus c minimum 1. And this you need to check. This is a fact just in real numbers, right? For any number x, y, z, you have this because this function a minimum 1 is subadditive. Subadditive. So its value at a plus b is less than its value at a plus its value at b. So here your a's are this, this, and this. Okay. Or maybe in absolute value, right? Sorry, in absolute value. So you can just check this. It's OK. And then if you take expectations, you have just triangle inequality. Okay. Let's look at A. I'm going to call it A prime because A will fail. So if you have x and y are equal, then their distance is just 0, right? Because x and y are equal, this is 0. 0 minimum 1 is always 0. So expectation of 0 is just 0. Expectation of 0 minimum 1 is 0. If you have dxy equals 0, this means expected value of x minus y minimum 1 is 0. And this is a non-negative random variable, a positive random variable. So if you have a positive random variable whose expectation is 0, what can you say about that random variable? If you have a positive function whose integral is 0, what can you say about that function? The function must be 0 almost everywhere, or here almost surely. So x minus y minimum 1 is 0 almost surely. So from this, you can conclude that x and y are equal almost surely. That's why A fails, and I called it A prime. So we only have, so dp is not a true metric due to A prime, which says x, distance between x and y is 0 if and only if they're equal almost surely. Almost surely. I always used d. I should have used dp. Yes. Okay. One more. Oh, no. Okay, dp. Good. Good. Anyway, so there is just minor issue here, okay? So it's not a big trouble. What we do in probability is to define a relation on L0 by the following. So we call x and y are equivalent if and only if x and y are equal almost surely. Okay. What kind of a relation is this? Do you remember modular arithmetic? 1, 4, 7, they're considered the same modulo 3, right? 0, 3, 6, 9, they're considered the same modulo 3. So that kind of a relation is called an, what kind of a relation is that? Equivalence relation, right? So this is an equivalence relation. Is an equivalence relation. Let me write it in full. Equivalence relation on L0. And the property of equivalence relations is that it partitions your world into equivalence classes. Okay? So let L0, without the script L, just the usual L, be the set of all equivalence classes of this equivalence relation. Okay. What is this equivalence class? What is an equivalence class? Well, it is simply a set of random variables, and in that set, all random variables, so take any two random variables, they're equal almost surely. They're equal almost surely. So I see two random variables that are equal almost surely as a single random variable. That's what we do. So L0 can be seen as the set of all real valued random variables where two random variables are considered the same if they are equal almost surely. Okay. Now, why do we do that? Now, we have, now we may see dp as a function on L0 cross L0. And this way, it satisfies A, dp xy equals 0 if and only if x and y are the same in L0. In L0, meaning that almost surely. Okay? So now, in this new space, L0s are here. In this new space, things are identified up to almost sure equality. So two random variables are equal if they're equal almost surely. Okay? So this is like in modular arithmetic, you have equivalence class 0, okay, in which you have 0, 3, 6, and 9, and so on, are considered as just 0. So they're all 0. Okay? For you, there are only three numbers, 0, 1, 2. Okay? 1 is equal to 4, 4 is equal to 7, 7 is equal to 10, etc. So now we have x and y are equal if they are actually equal almost surely. Okay? And for probability, it doesn't really matter because for this distance, it doesn't really matter because if you replace them with two other random variables that are equal to x and y almost surely, you would get the same expectation. Because expectation is insensitive, right? If you play with those functions on a null set, your end result doesn't change. Okay? So it's not an invalid, annoying operation. It's just a valid operation. Okay? And this is a standard in probability. So in some papers, you rarely see this L0, but most of the time you see this L0. And at the beginning of papers, you can see statements like, okay, let L0 be the set of all real-valued random variables up to almost sure equality. Two random variables are identified if they are almost surely equal, etc., etc. Okay? Okay. So the whole point of doing that is that now we have a metric space. Is a metric space. Okay? A, B, C are all satisfied. And even we have that xn converges to x in probability if and only if the distance between xn and x converges to 0. This kind of probability is converging to 0. And this is about expectation of xn minus x minimum 1 converges to 0. So we need to show that these two things are equivalent. The nice thing is that both have xn minus x in absolute values. Okay? But this is in expectation, this is in probability, but I can see it as an expectation, right? So it boils down to comparing the functions indicator epsilon to infinity and the function something minimum 1. Let's say z minimum 1. So let's draw a picture. So z minimum 1 is this, right? It is linear up to 1, and then it's constant. How about indicator epsilon to infinity? Well, let's say epsilon is here. So it is 0, and then it is 1. Okay? So we cannot say that one is always greater than the other. Because here this is bigger, here this is bigger. What we can do is to shift the indicator function by epsilon. Just shift this by epsilon. So if you shift it by epsilon, it's going to touch exactly this line, right? Just shift it by epsilon. Shift this part by epsilon as well. So this is going to be epsilon plus 1, right? In this case, So in this case, we have this z minimum 1 is less than epsilon plus indicator epsilon to infinity, right? So if you take z equals absolute value xn minus x and take expectations, you would get this, right? Expectation of indicator is just probability. So in other words, if you have xn converges to x in probability, meaning that if this converges to 0, by sandwich theorem, this also converges to 0, right? So convergence in probability implies convergence in this metric. This is the metric. For the converse, there is a similar idea, okay? The idea is that, so let me write it in blue maybe. You can also check that this is less than epsilon times the indicator. You can draw the picture for that blue curve, okay? You can draw a blue curve here. And if you do that part, you would get epsilon times probability xn minus x greater than epsilon. And this is positive, right? This is positive. It's just epsilon times probability. So the thing is that the metric is upper and lower bounded by the probabilities in some sense. So if you have convergence in probability, then you have convergence in this metric. If you have convergence in this metric, then you have convergence in this probability. Just apply sandwich theorem twice, right? So apply sandwich theorem here. If we apply sandwich theorem here, dp xn x to 0 implies convergence in probability. And if we apply sandwich theorem here, then you have xn converges to x in probability implies convergence in this metric. So these two are equivalent. A beautiful consequence of this is that limit in probability is unique. So meaning that if xn converges to x in probability, then xn converges to y in probability. So if you have possibly two limits, then they're equal. Well, let me put almost surely, or you can say they're equal in L0, the new L0. Okay, why is that true? Why is that true? Well, just look at the difference between x and y. Use triangle inequality with the p metric, okay? So x and xn plus xn and y. This converges to 0. This converges to 0. This means the distance between x and y is just 0. So x and y are equal almost surely. So I just tried to convince you that convergence and probability is not something weird. It is, in fact, you can just see it as a special metric space, right? Special metric on L0, right? So in your analysis class, maybe you have seen a lot of examples of convergence types, right? Like different metrics, examples of different metrics. So you show that something is a metric space, some function some function D is a metric, and then this gives you a notion of convergence. And indeed, convergence and probability is one of those notions that you can write in terms of a metric. Okay? And it is weaker than almost sure convergence. Okay, so that's all we know. So now we're going to pass to another notion of convergence, which is convergence in LP. So sometimes you have things like the expectations converge, but the sequence itself doesn't converge. Okay? The variances converge, but the sequence doesn't converge. So to talk about convergence of expectations and variances, we introduced this notion of convergence in LP. Okay? So convergence in LP. First of all, I have to tell you what LP is, right? So let's first talk about LP spaces. So let's say we have a probability space omega fp, and we have the space of random variables that are identified almost surely. Okay? So for x in L0, define, let also be p be some number between 1 and infinity. Okay? Let's fix a p. So p is going to be some power, okay? Some power. Like if it's 1, it's going to give us some expectation. If it's 2, it's going to be related to second moments or variances. So define the p norm, LP norm of x as follows. So it is the expected value of the pth power of the absolute value of the random variable. Okay? This whole thing is raised to power 1 over p as a normalization. Okay? So since absolute value to some power is always positive, this is an expectation of a positive random variable, which is positive, including plus infinity. So now we'd like to make sense of it as a norm. And you know, norms cannot be infinity, right? Norms cannot be infinity. So we define the space of random variables whose LP norm is finite. This way, this norm can be something that is finite. And what we would like to say is that it is indeed a norm. Okay? So LP with the norm LP norm is a normed vector space, in the following sense. So it's a vector space. It's a vector space on which you have the norm with the following properties. So the norm is 0 if and only if the function is 0, but it is in the L0 sense, so it is almost surely, it's fine. Now we have the L0 space, it's fine. Another one is a scaling of a norm, right? So if you look at constant times x, its pth norm should be the absolute value of c times the norm of x. This is very easy to see. Just put an x, just put a c here. Let's say you multiply it by 2, okay? Let's say you have 2 here. Then this goes out as 2 to power p. And since you raise it to power 1 over p, you get rid of that. It's just going to be a 2. 2 to power p, to power 1 over p, it's going to be 2. So this is just easy to check. Easy to check. This is also immediate, right? Expectation is 0 means that the random variable is 0 almost surely, because the random variable itself is positive. Okay? So the last thing is, again, the triangle type inequality. So the norm of x plus y is less than the norm of x plus norm of y. We're going to show it soon. We're going to show it soon. For now, let's take it for granted. And we now have that LP with its LP norm is a vector space. So the special cases are, the two important special cases are 1 and 2. So in the case of 1, you have just random variables with finite expectation, right? Integrable random variables. I guess we defined it as L1, right? We called it L1 at some point. And 2 is the ones with finite second moment. So then you can also check that it has finite variance, because variance is just this minus this squared, right? So square integrable random variables. This is called square integrable. Okay. And we will also define the case p equals infinity. Okay, we need to treat it separately. And this is called the L infinity space. Okay, so now let's take p equals plus infinity. And we're going to define the L infinity norm of x as the essential supremum of the absolute value of that. What is the essential supremum? So it is the supremum, it is the largest value that the random variable can take, but it can exceed this value on a set of measure 0, on a null set of probability 0. Okay? So in other words, if your random variable is generally bounded, but takes some crazy values on a set of probability 0, you still call it bounded, or essentially bounded. Okay? So this L infinity norm just looks at the minimum number such that x is bounded by c in absolute value almost surely. So this is the minimum upper bound, but almost sure upper bound that you can find. Okay? This is the precise definition of that. So when so let's define L infinity as the space of random variables that are bounded, essentially bounded. So space of essentially bounded random variables. That's the most convenient space of random variables, because if you have boundedness, then you have finite expectation, finite variance. So this L infinity is a subset of all other LPs. Okay? So if you want to prove something for random variables, if you want to create some setup for random variables, the simplest setup is perhaps this L infinity, if you want to work with general probability spaces. Okay? So essentially bounded random variables. And again, L infinity with the L infinity norm is a normed vector space. Normed vector space. So this means we have LP spaces with the, for the cases p between 1 and plus infinity, right? These are the spaces that we obtained. So are all Banach spaces. What is a Banach space? Well, we know that it has a norm. This norm is complete. This norm is complete. What is complete? What is complete? Every Cauchy sequence is convergent, right? Okay. So that norm even satisfies this property, but we're not going to prove that. So what is next is some inequalities that will help us to prove this triangle inequality. Okay? And on the way, we're going to prove some very useful inequalities. So next time, we're going to prove the following inequalities that are very famous. Jensen's inequality, or Jensen's inequality, Hölder's inequality, and Minkowski's inequality. And also Lyapunov inequality. So these are all some famous inequalities. So we're going to start by proving them. We're going to prove the first one first, and then the rest are going to be just consequences of Jensen. Okay? So let's stop for today. Okay, thank you.